Hello guys, in this video we're going to discuss about astrophysics. So what is astrophysics? Astrophysics is a branch of astronomy concerned with physical nature of stars and other celestial bodies, and the application of laws and theories of physics to interpretation of astronomical observation. There are a lot of topics in astrophysics, but we're only discussing about Einstein's equation, trigonometric parallax, redshift, which you have known in our discussion about cosmology, and standard candle. So our first topic is Einstein's equation. We all know Einstein's equation as E equal to mc squared, where E is our energy and m is our mass and c is speed of light. But the real equation or the symbol for this equation is this one. It's the change of energy equal to the change of mass times the speed of light squared. So we all know that c is speed of light, which has a value of 3 times 10 to the 8 meters per second. And this change of mass, it's actually an additional mass if the mass is moving. I will explain this further later. So when the mass is moving, it could create kinetic energy, potential energy, or internal energy. And this mass is very small. It's negligible. You don't record it. But Einstein see this as something, this extra mass. And finally, we have change in energy. It's actually an extra energy. It's either kinetic energy, potential energy, or internal energy. So to further explain this, some theories or they said that the change of mass is equivalent or can be converted to energy, the change of energy. Some sources also believe that you cannot convert mass to energy, but the most accepted one is converting this extra mass to change of energy, either kinetic, potential, or internal energy, or from energy converting it to extra mass. Suppose you have a mass. So if this mass is at rest, it doesn't do this equation. It doesn't involve in this equation. So if this mass is moving, then therefore it will have this equation and it will create either kinetic, potential, or internal energy. So if this one is moving or it radiates or creates light like our sun, it actually gives off energy, which is this extra energy. And when you give off extra energy, then you will lose a mass. Scientists actually told that the mass of the sun is decreasing by a very small percent. It's actually very small. You cannot hardly change the mass of the sun. So this is also the reason why the atomic bomb is created, and Einstein is very disappointed with this equation because with this equation atomic bombs are created, and this equation that Einstein did only took him 3 pages. His equation is in this form, which entails that mass is, or the change of mass is equal to the change of energy. So again, if this mass is not moving, therefore it doesn't give off energy, and it doesn't give off also its mass. So there are actually a debate on whether we can convert mass to energy. Next is the trigonometric parallax. It is used to measure distance of a nearby stars. So the nearest star from our sun is the Proxima Centauri. It's about 4 point something light years away from Earth. Parallax is a displacement or difference in apparent position of an object viewed along two different lines of sight, which create an angle of inclination. So there will be a video to explain this one further. We have distance conversions here. AU is the astronomical unit, 1.496 times 10 to the 6 kilometers. So this is usually known as the distance from Earth to the Sun. One astronomical unit is the distance of the Earth from the Sun. The next conversion is light year equals to 9.461 times 10 to the 12 kilometers. And you all know the parsec. So if you're going to say megaparsec, it is just 3.086 times 10, so minus the million, which is converted for mega, 10 to the 7.
Have you ever traveled down a road in a car and looked at the mountains or hills in the distance? If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower, and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seem to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the Sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the Sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the Sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the Sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
Okay, so that's how parallax work. So if you might ask how are you going to determine the angle? The angle is when you position your telescope, there will be a particular angle to point the star. So that angle will be recorded from the time you have point the star after 6 months. So you need to point again the stars and record the angle. So with these two angles, you can have this combined angles and can solve the distance of the star. So that's how you're going to get the distance of the nearby star. The next is redshift. If you have known already in our discussion about cosmology, It is a displacement of spectral lines towards a longer wavelength in radiation to distant galaxies and celestial objects. So shifting light wave to red spectrum. Example for that is to a longer wavelength or a lower frequency. Calculating the redshift velocity. So how did Hubble um, come up with the Hubble constant and calculating the redshift velocity? It's actually the change of the wavelength using the Doppler shift. So using this Doppler shift, he uses the Doppler equation, which is given as this one. The change of wavelength over the first recorded wavelength equals to velocity divided by speed of light. So arranging the equation, we can arrive at speed of light times the change of wavelength over the first recorded wavelength equals to our velocity. Example, two wavelengths are recorded by an astronomer as the galaxy redshifted from 395 nanometer to 420 nanometer. So if you're wondering what are those, it's actually the spectrum on the light, if you can recall. So calculating the difference of two spectrum, you will have 35 nanometers, and then put the first wavelength, which is 395 nanometers, then multiplying it with our speed of light gives us 2 times 10 to the 6 meter per second, or converted to kilometers per second, it's 2000 kilometers per second. And the nearest star is actually 30 megaparsec. So if we divide it with 30, it will give us 6.67 kilometers per second per megaparsec. So it's actually near the equation of Hubble. So this is to explain further what is a redshift.
What is redshift? So this is going to be quite a quick video, basically explaining what redshift really is. So astronomers often use the term redshift to describe how far away objects really are. To understand what cosmic redshift is, we must think about sound. A great example of this is a police car. You hear its siren because the waves travel through the air into your ear. If the police car is moving, then the sounds in front of it are compressed and create a higher frequency sound, and the sound waves behind it are stretched out, creating a lower frequency sound. As the police car passes in front of you, you would hear the familiar Doppler shift. Light is quite similar. It also travels in waves, and it's quite a similar process to what is happening within the waves. Light waves are able to be compressed and stretched, just like sound. But with sound, you would change the frequency, but with light, you change the color. Blue light has shorter wavelengths than red. When an object in space moves towards us, the light waves are compressed into higher frequencies, and this is why the light is blue shifted. It's shifted towards the shorter wavelengths. But when an object moves away from us, the light waves are now stretched. These waves now go into the lower frequencies, and this is what's known when light goes to redshifted. It shifts to the longer wavelengths.
So the last topic is the standard candles. It's used to measure distance of farthest galaxies or stars that parallax are too large to measure. So there is a limitation on parallax. So this standard candle is used to measure these vast or farthest galaxies or stars. Is distant star of known luminosity. So how bright is the stars or galaxy? So there are two types of standard candles, which is the Cepheid variables, which is 30 megaparsecs away from our sun, and we have type 1A supernovae. It took us about a 10,000 megaparsecs of distance. Here's a video to further explain the standard candles.
Standard candles are objects whose intrinsic brightness or luminosity we know really well. For example, if you know how bright your light bulb is, and you ask your friend to hold the light bulb and walk away from you, you know that the amount of light you receive from your friend will decrease by the distance squared. So by comparing the amount of light you receive to the intrinsic brightness of the light bulb, you can then tell how far away your friend is. In astronomy, our light bulb turns out to be a special type of star called a Cepheid variable. These stars are internally unstable, like a constantly inflating and deflating balloon. And because the expansion and contraction causes their brightness to vary, we can calculate their luminosity by measuring the period of this cycle, with more luminous stars changing more slowly. By comparing the light we observe from these stars to the intrinsic brightness we've calculated this way, we can tell how far away they are. Unfortunately, this is still not the end of the story. We can only observe individual stars up to about 40 million light-years away, after which they become too blurry to resolve. But luckily, we have another type of standard candle, the famous Type 1A supernova. Supernovae, giant stellar explosions, are one of the ways that stars die. These explosions are so bright that they outshine the galaxies where they occur. So even when we can't see individual stars in a galaxy, we can still see supernovae when they happen. And Type 1A supernovae turn out to be usable as standard candles, because intrinsically bright ones fade slower than fainter ones. Through our understanding of this relationship between brightness and decline rate, we can use these supernovae to probe distances up to several billions of light-years away.
So that ends our topics about astrophysics. So I hope you have understand our discussion and learned something. And if you have any comments, feel free to comment below